In this class, I will explain the basics of kinematics of fluid flow. So, in mechanics, in mechanics is divided into two groups. That is classification. One is called as the statics, and another is dynamics. And once again, dynamics is divided into two parts. That is kinematics and kinetics. Just like as in the case of solids, in the case of fluids also, we can classify fluid dynamics into fluid kinematics and fluid kinetics. So kinematics, it deals with the path traced by fluid particles, distance travelled, displacement, velocity and acceleration. So only these physical phenomena are considered in the case of kinematics. So we are not dealing with energy and forces. So forces and energy, they are not considered or not considered. So in the case of kinematics, whereas if you consider the cause for the flow, that is the force causing the flow and also energy involved in the flow, then it becomes kinetics. Now here we discuss only about velocity and acceleration part. As you know, velocity can be defined as the rate of change of displacement, or it can be displacement divided by time. Its SI unit is meter per second. And acceleration is rate of change of velocity, which is changing velocity divided by time. Unit is meter per second square. Just it is similar to the case of solid mechanics. Now to understand the velocity concept in the case of a fluid flow, I will consider a particle P in a fluid. In a fluid flow. So fluid is flowing in a pipe or a channel, let us say. I will consider a point P in that flow with coordinates x, y, z. So whenever you are speaking about a point, you have to specify the point with respect to space coordinates. So x, y, z, I will take it as a three-dimensional coordinate, Cartesian coordinate. X, y, z, they are the coordinates of P with respect to the reference axis x, y, z axis. Now when the fluid is flowing, it will be having three components of velocity, one along x direction, which I denote it as u, another along y direction, which I denote it as v, and another along z direction, which is taken as w. Since u, v, w, they are all vector quantities, I have shown them by arrows, because velocity is a vector quantity. So that can be written vectorially like this. Your total velocity at any point, or the resultant velocity at any point, v, capital V, can be written as ui plus vj plus wk, where you know that in vector algebra I, j, k are the unit vectors acting along the x, y, z directions respectively, and the magnitude of the resultant velocity or the total velocity v is denoted like this, modulus v, or v simply v, which is given by root of u square plus v square plus w square. These things you have learnt in vector algebra. So v gives the magnitude of velocity. That means if you know the velocities in the three directions at a particular point, you can always compute the resultant velocity or the total velocity at that particular point. So you know that this u, v, w, they are all functions of x, y, z and also t, very important. So whenever you are speaking of fluid properties, we have to speak of fluid properties with respect to two things. One is about the space, at what point you are considering in the flow, and another thing is about the point, at what time you are taking the velocity. So both position and time, they are important. We call them as space coordinates and time coordinates. So therefore, these components of velocity u, v, w, they are all functions of x, y, z and t. Now to define u, v, w, we can use the mathematical representation using differential calculus, what we have done in the limits. So u can be defined as limit dt tending to 0 dx by dt, v can be defined as limit dt tending to 0 dy by dt, w can be defined as limit dt tending to 0 dz by dt. When you talk about this is called as the instantaneous velocity. Instantaneous velocity. That means when the time is very small, dt tending to 0, whatever velocities you get in xyz directions, they can be defined like this. Here dx, dy, dz, they are all displacements along xyz directions in time dt. So this is the mathematical calculus way of expressing the components of velocity. Now I will take a simple example. So in a fluid flow, you have the components of velocity given like this. U is x square minus y square, v is y square minus z square, w is z square minus x square. So as already told, they are functions of x, y, z. And sometimes they will give in terms of t also if the flow is unsteady. I will come to that later. Now if you want to find the total velocity at a point 1, 2, 3. So x is equal to 1, y is equal to 2, z is equal to 3. How to find that? So what we have to do is, given the expressions for u, v, w, and given the point x, y, z, you can always calculate the components by substituting the values of x, y, z here in these expressions, and then by using this equation root of u square plus v square plus w square. If you apply that, you can see here u is given as x square minus y square, x is 1 here, y is 2 here, z is 3 here. If you substitute that, 1 square minus 2 square, you will get 4 square of that, because u square I am taking, plus v square, v means it is y square minus z square, that is 2 square minus 3 square, square of that, plus w is z square minus x square, that is 3 square minus 1 square. If you simplify that, you are going to get root of 98, that is 9.9 units. So it may be in meter per second or centimeters per second, whatever it is. So that's why I have written it as units. So this is how you can find out the magnitude of the resultant velocity as the total velocity as the net velocity at a particular point in a fluid flow by knowing the components of velocity at that point. Now coming to the types of flows, very important question. So types of flows, in fluid flow, we can classify fluid flows into 5 types. 5 types based on different criteria. As I already told, these fluid properties in a flow, they may vary with respect to 2 things. One is with respect to time, another with respect to that position or the space. So time is nothing but t here. I will take time coordinate as t. Space coordinates I will take it as x, y, z. Now, the first classification deals with respect to time. So if the fluid properties won't change with respect to time over a particular interval of time, over a particular time period, then the flow is called as steady flow. That means here fluid property means we can take it as fluid properties can be velocity, it can be pressure, it can be density, etc. So these are the fluid properties. Normally, mainly because we are treating with civil engineers, we treat with liquids. In the case of liquids, this rho density normally won't change. So that's why main thing here is this v, velocity. So velocity of flow may vary from time to time, or it may be constant with respect to time over a time period. So for example, now velocity of flow is something 1 meter per second. After 1 hour also it is same, 1 meter per second only. Then you can say that the flow is steady. That is the meaning of that. So mathematically you can represent like this: dou v by dou t is equal to 0. I am using the term dou here instead of d because here this v depends on so many parameters. It depends on x, y, z, it depends on t. That's why I have taken the partial derivative. So if this is 0 means, what is the meaning of this? Velocity remains constant with respect to time. That is why its derivative is 0. Suppose if the velocity varies at a particular section from time to time, then we say that it is unsteady flow. So where the derivative is not 0. Now coming to uniform flow, second classification is uniform flow. This is with respect to position or space. So I will consider a length of the pipe. I will take 2 sections or 2 points in that pipe separated by some distance. If the velocity doesn't change over that length, so that means if the velocity remains same at both those 2 points, then we say that the flow is uniform. Suppose if the velocity changes at different sections in a flow, at different points in a flow, then the flow is called as non-uniform flow. I am using a S here. S represents space. So it can be with respect to x, or it can be with respect to y, or it can be with respect to z. So in practical cases, we can have all these types of flows. The third classification is laminar flow and turbulent flow. This you have learnt in the first module, that is first chapter, when I explained about Newton's law of viscosity. So I considered the flow as laminar flow. So laminar flow means, suppose if this is a pipe through which some liquid is flowing in this direction. So if the flow takes place over laminae or layers, so that means one layer above the other. The meaning of that is it has got a high resistance to flow. So viscosity is very high, mu is very high. So mu acts in the opposite direction, that is which results in the case of a shear stress, tau. So if tau is very large, if the value of tau is high or mu value is very high, that means in the case of a thick oils and real fluids, you can say. So in such a case, this type of flow can happen. So flow is not haphazard. It is taking place like one layer above the other like that. So this is how we can show a laminar flow. So this can happen in the case of a thick oil or a real fluid whose viscosity is very high. Coming to the other way, turbulent flow. So in the case of turbulent flow, for example, water which has got very low viscosity, a fluid which has got very low viscosity, which won't offer much resistance to flow. Tau value is very less, mu value is also very less. So when mu is less, definitely tau will be less according to Newton's law of viscosity. So we know that tau is equal to mu times dV by dy. This is the Newton's law of viscosity, which I have explained in the earlier lectures. So if this tau is very less, then what happens if I have considered the example of a channel. So this is sloped channel. So in the case of a sloped channel, you can expect a turbulent flow. For example, water. So let us say the slope is some 1:50 or 1:100, something like that. When water flows down this, you can observe that there will be some turbulence effect. So this whirling effect or turbulence effect will be there, so which result in eddy currents. So these are called as eddy currents. If this type of flow occurs, where the flow does not take place as in the form of layers or laminae, where there is eddy currents formation will be there, turbulence will be there, then such a flow is called as turbulent flow. So this type of flow can happen in the case of low viscous fluids or ideal fluids, or best example is water. Now coming to the fourth classification, rotational and irrotational flows. Suppose in the flow, if the fluid particles during flowing rotate about their mass centers, then the flow is called as rotational flow. So this can happen in the case of thick oils, once again in the case of real fluids. The fluid particles may rotate about their mass centers. For example, if the velocity is very less, just as in the case of laminar flow, so then this type of flow can occur. So a laminar flow can also be a rotational flow. Coming to irrotational flow, if the fluid particles, if they don't rotate about their mass centers during flow, then it is called as irrotational flow, and this can happen in the case of ideal fluids. For example, best example is water. Now coming to the last classification, it is one-dimensional, two-dimensional and three-dimensional flows. So which can be represented mathematically like this. So I have already told that the fluid particles, they depend on the position of the fluid particle, space coordinates and the time. So if the fluid particle, here symbolically this V stands for the fluid property of fluid particle. This can be anything, this can be rho, this can be P, anything. Just to understand, mainly we consider about the velocity in the kinematics this thing. So therefore, V is equal to F of x. That means, if the velocity of flow depends only on one space coordinate, then it is called as one-dimensional steady flow, because it is independent of time. If t is also included, if v is a function of both x and t, then it is one dimensional because only x is there and t is also there, therefore it is unsteady flow. Unsteady flow means, so it is giving the velocity is varying with respect to time, that is why v is a function of time. Similarly, for two dimension you have to take x, y. So if the velocity is a function of two space coordinates, then f of x, y, then it is two dimensional steady flow. In addition to that, if t is also included, then it is two dimensional unsteady flow. For three dimensions, similarly, velocity is a function of all the three space coordinates x, y, z, then it is 3D steady flow. If t is also included, then it is 3D unsteady flow. So these are the five types of classification of fluid flows, very important question. Now I have taken two examples here. The first example here, I have taken a uniform pipe or a prismatic pipe. Prismatic, uniform diameter pipe or a prismatic pipe. Prismatic pipe means diameters remain same. Suppose if Q is the flow or the rate of flow, we call it as discharge also. So if Q is the rate of flow in this pipe, so since the diameter remains same here, area also remains same and velocity also remains same. So here and here. Neglecting the losses, frictional losses, so we can take the velocity at this point at 1 and velocity at 2 as same. That means it is not varying. Then in such a case, this is an example for steady uniform flow because velocity remains same at both these 2 points over a length. So uniform flow. On the other hand, if I take a tapering pipe means non-uniform diameter. So diameter at this end is d1, diameter at this end is d2. So here also I will take here. So this is section 1, section 2. In this case, what happens? Whatever V is there here, it will not be the same as V here. So V1 and V2, they are different here because area is different. So because Q is A into V, that I am going to explain in the next lecture. So this discharge is given by cross-sectional area of flow multiplied by the velocity at that section. So then, since here A1 and V1 and V2, they are different because A1 and A2 are different. A1 is pi d1 square by 4, A2 is pi d2 square by 4. Whereas here area is same, pi d square by 4 at both the ends. Since velocities are different over a particular length, it becomes non-uniform. It may be steady. It is steady because I have taken constant discharge here. If the discharge is constant, we say that it is steady flow. Please note that point. If the discharge varies, it becomes unsteady. Now here, since discharge I have taken Q as constant, so in this case, for a prismatic pipe having same diameter throughout, it becomes a uniform flow. Whereas in the case of a tapering pipe, it becomes a non-uniform flow because the velocities at the two different sections are different.